All right, so my name is Mish Hiftihiv. I'm a researcher at JetBrains Research at the Machine Learning for Software Engineering Lab and also at the Intelligent Collaboration Tools Lab. And today I'm going to talk about our work on metrics quality for code generation models that we are doing together with Igor Bogomolov, Yaroslav Sokolov, and Timofey Bryksin at the ML4SE lab. So in this talk, I'll first briefly introduce the problem of code generation. What is it, why it is important, and why metrics matter. Then I will cover the current status of the code generation problem and also elaborate on our motivation for the study. Then I will describe the metrics that are commonly used in the community, the metrics that have been recently proposed, and the metrics that we have considered. I will then continue with describing the code generation models and datasets that we have studied in our research. Finally, I will explain our research methods and cover the results we have obtained so far, and outline the questions we haven't still fully covered and possible future work directions. So let me start with introducing the problem. So the code generation problem is a problem of generating programming code from the natural language intent. And its significance have been understood at least 35 years ago by Balzer. Well, it is the simplest example that I can think of is like the user writes, sort me a list called lst, and then the program yields lst.sort in Python. If code generation is well implemented, it would greatly reduce the cost of creating new programs. It will simplify code maintenance and will attract new programmers who may have limited programming experience. Thus, we can argue that the code generation problem is quite literally $1 billion question, and working on code generation models may be useful and profitable. Okay, so the current status of the problem. First of all, I should mention that somewhere in the utopic land, there exists a marvelous and awesome model called GPT-3. This is claimed to generate many lines programs that satisfy a short and fuzzy natural language intent. So a user types something like, I want a site, a website with such a button and such a response for the button click, and GPT-3 manages to yield the exact JavaScript code for this website. Unfortunately, the model is not freely available. It's been almost a year since I've sent a request to see a private beta. I guess the else are still stuck in the traffic jam. The other models that are freely available are unfortunately not that impressive. For example, let us consider the task of generating a Python one-line program from the Stack Overflow question, which is used as a natural language intent. So an example that could be thought of is split a multi-line string called input string into separate strings, and the proper answer being input string dot split parentheses /n. So 30% of the snippets that are generated by the best model currently available are okay or almost okay. 55% of the snippets are practically useless. They're either gibberish or hardly related to the problem. And in 15% of the cases, the snippets were wishy-washy. And for example, the question and the snippets that I have presented are like mediocre for the problem we considered. So even though the task seems to be kind of simple, I mean, the Python code is really very short and the intent seems to be really well written, the current state-of-the-art model that is publicly available is not really able to generate something useful. Okay, so let us continue with metrics for code generation. So right, we got some code generation model. We developed such a model, and we want to measure the quality of the model. We want to check if it is indeed training, so the score on the validation dataset is improving, and whether, say, our choice of hyperparameters was meaningful. So a golden standard of quality is an opinion of an experienced programmer. Well, unfortunately, this standard is almost always impractical. I mean, we can, a typical model has like 30, maybe 50 epochs, and after every epoch, we are doing a validation. So we can't really ask an experienced programmer to grade 30 times 500, which is typical size of test data set, which is 15,000 generated snippets. It's just impossible. This means we need some kind of a metric. That metric should be very good at emulating programmer's opinion and should be able to tell us which model is better. So a formal definition of a metric is a function that takes a generated snippet, compares it to a set of references. Usually I will consider that there is only one reference, which is most often the case for the code generation. And then this metric yields a number from 0 to 1. So it's not true for every metric, generally it is the case. And the higher score of metric corresponds to the higher quality of the snippet. So for the metric to be effective, at least the 3 following requirements should be satisfied. First, metric should be suitable for the assessment of the code generation models. Second, the difference between the results of various models should be statistically significant. And third, the metric scores should correlate with the human judgment. Okay, so why these requirements? So let me note that some of these requirements may seem redundant, and I will explain now why exactly these requirements. We obviously shouldn't use a metric that is unsuitable for code assessment. However, if we go back for a second, the statistical significance and correlation with the human judgment is not enough to claim that the metric is suitable for the code generation assessment. I mean, let us take it is possible that the metric is just performs okay for the datasets and models that we are studying. But if we consider some other model or some other dataset, then our metric will fail. Let us take an extreme example. Let us imagine that there is only one dataset and only 2 models available. Only one dataset and only 2 models available. And one of the models produces complete gibberish on any input from the dataset. Like, it's not even compilable, it's not even programming code in any sense. And the other model always produces a perfect code. So like the example is in the slide. And in this case, any metric that is good enough to award 1 to a perfect snippet and 0 to a snippet that has no semblance to a reference whatsoever will have a perfect correlation with the human judgment and perfect statistical significance for distinction between models A and B. However, these results, they tell us nothing about the actual performance of the metric. And in some other situations that may arise with another dataset or another model, everything may change. For example, we want our metric to be to have monotonic relation metric score to be in monotonic relationship with the real generated snippet quality. Okay, the real generated snippet quality is a murky subject. It's even hard to define whatever that may be, but well, we still kind of understand what's that exactly, and we do want that for a better snippet we have a better grade. So while the example I've presented is not very realistic, in practice we have a very significant scarcity of publicly available models and datasets, and so this scarcity makes the scenario that everything seems quite okay for the metrics we are given, but in fact it may break somewhere at some point. The scenario is quite possible. So let me give a more real example. So let us consider the BLEU metric. The BLEU metric was created for the neural machine translation for the natural languages. It is currently the de facto standard for the code generation model quality evaluation. I will give a proper definition and explanation later. For the current discussion, let me just state that BLEU compares N-gram overlaps between references and generated snippets. Naturally, it's not obvious that the metric that works well for the natural language translation should work well for the code generation. And so let us consider an example from the real dataset and real models. So we have a code generation task, which is to concatenate a list of strings. We have a reference, which is perfectly working, and we have a code snippet that has been generated by a model. So the code snippet, as you can see, is a complete nonsense. well, it doesn't solve the problem, but this is okay for the code generation models, but it misses almost everything. It doesn't even manage to reproduce the list of strings. It yields a set instead of a string, and so on and so forth. So a human programmer will probably give this the snippet a 0 score because because this. I'm sorry, guys. Just a second. The human programmer will give the snippet probably a 0 score because it's completely relevant to the problem. However, the BLEU score, according to the common way of computing BLEU, is 0.48, which could be treated as we are halfway there, but we're not really. For another example, we have a task which is to remove a key C from the dictionary D. We have a reference, and we have a real generated snippet, which kind of just took another way to solve the problem. But it's still okay, it still works. And we see that the BLEU gives this working snippet a 0 score, even though the snippet is perfectly fine. So we can see that even if metric is widely accepted, is believed to be good enough for the task, and even if people are considering that it is statistically significant and so on and so forth, it doesn't mean that it actually works. Now, the cases that I've presented, they're just anecdotes. It's not a real proof. And it is indeed unclear how to generally prove that the metric is suitable for the code generation task, or probably any other task. But it is possible to collect some anecdotal statistics. It is possible to collect data on correlation with human judgment across the most diverse and various datasets, and kind of increase our trust in the metrics that we are using. And we can also do some checks that will show that the metric is bad for assessing generated code. And if all the checks are passed okay, then we probably can say that, well, all right, most probably the metric is going to be okay. All right, second issue with the metric pertinence and the comparison of metric scores is the issue of statistical significance. The current way of using metrics for models assessment assigns single number to each model output on the test dataset. So it's like we average the metric score over the whole dataset, and we say that this is the result. So this approach is really simple, and it may be very practical during the training process, because we just need to figure out which model is better, and whether we do want to do an early stop, or we want to roll back to an earlier checkpoint or something like that. But it is not really clear how the difference in the metric score can be translated into statistical statement. So, I mean, standard approach is quite literally like two models we created had BLEU scores 30.26 and 30.69, so the latter is better. And I need to give a note that for the dataset comparisons, the metric scores are usually multiplied by 100. So, I mean, there is indeed a difference, but it's not clear how statistically significant it is. And if there are no further checks, such as Wilcoxon sign rank test, we can't really say that our improvement is statistically significant. So it is really important to study how big the difference between the scores of two models for a particular data set should be for us to claim that one of the models is better than the other with the desired confidence. And here I need to make a side note that unfortunately is going to crop up quite a lot, is that there is really a big problem of models availability. In many cases, people publish their study, but they don't publish their models or the outputs of their models. So there is a really solid motivation for the researchers, even those who do publish their models. There is a real motivation for this researcher not to care too much about the Wilcoxon tests and other statistical tests, because they're simply unavailable for comparison with many other models. Okay. So the third issue with the metric applicability is the correlation with the human judgment. So most of the metrics that we will discuss in this talk have been originally created for a narrow application, such as assessing quality of a natural language translation, or maybe checking the quality of code translation, And afterwards, they were adopted for some other tasks. So the original papers that introduce these metrics, they usually include some kind of a study that show high correlation between the metric score and the human judgment. However, it is not clear that adopting these metrics for some other task will be actually solid. For example, let us consider the BLEU metric. So it has been created for the natural language translation and has been shown to work quite well for the task. But there is no data on correlation between metric scores and human judgment for code generation. Well, almost no data. There is a very recent paper on that, but I will cover that afterwards. There is very poor correlation between the BLEU and the human assessment for the text generation problem, with the better metrics being available. And there is a rather weak correlation for the code migration or code translation task. And better metrics are claimed to be available for the code translation task. So it's like we don't, there is a circumstantial evidence that BLEU might not be good for the code generation and no direct evidence in any direction. So this throws yet another shade of doubt on why we're using BLEU at all. Okay. So let us move on to the metrics discussion per se. In our study, we have considered 6 different metrics: BLEU, ROUGE-L, METEOR, Ruby, CodeBLEU, and BLEU. The first 3 metrics originate from the natural language processing domain, and they are the metrics that are used to measure the quality of code generation models. So the share of papers that feature either ROUGE-L or METEOR is very small. In practice, almost every paper features just BLEU. So this BLEU was created for the natural language translation, for the neural machine translation. ROUGE-L was created for translation and text summarization. METEOR was also created just for translation. Ruby is a metric that has been created specifically for the code translation task. CodeBLEU was created for a variety of code-related tasks, for the code translation, for the code generation, and the code refinement. And finally, BLEU is a mixture of Ruby and BLEU metrics that we surmise to be suited well for the code generation tasks. I will now describe some of the metrics in more details. So let us start with the BLEU. BLEU, a shorthand for bilingual evaluation under study, is based on the modified N-gran precision measure, with a length penalization for the candidate sentences that are shorter than the reference ones. BLEU scores are given by this equation. By the way, can you guys see my pointer?
That's видно.
Cool, thank you. All right, so the BLEU metric is given by this equation. So this prefactor here is called brevity penalty, and you can see that it penalizes the translation of the generated code sequence for being shorter than the reference. So C here is the candidate length, R here is the reference length, and BN here is a modified N-gran precision. So what is the modified N-gran precision? The usual N-gran precision is the sum of all occurrences of all correctly guessed N-grams in the candidate divided by the length divided by the sum of by the total number of N-grams in the candidate N. And the modified N-gram precision is all the same, but for every different N-gram, the maximal amount of times we counted is kept by the amount of times it appears in the reference. So there are various definitions of BLEU, but the standard definition that is used for the code generation tasks is using the following way to figure in the N-grams. So we consider 1 grams to 4 grams, and each N-gram has an equal weight, and we do and we consider the geometric mean of the 1 to 4 grams. Okay, so let me compute BLEU for a very simple example. So here we have a natural language translation. We have an obviously junk candidate, which is there repeated 5 times. And we have the reference, the cat set on the mat. So let us start with the brevity penalty. So the candidate here is shorter than the reference. So the brevity penalty is actually not 1, but something less than 1. For the 1 grams, let us note that the B1 is 0.4. So we have one kind of 1 gram in the candidate, which is there. And there is repeated twice in the reference. So when we compute B1, we should take the minimum between the amount of times there is repeated in the candidate, which is 2, and which is 5, and the amount of times is repeated in the reference, which is 2, and divided by the overall candidate length. This is how we get 0.4. Now the 2 grams, which are basically pairs of adjacent words, and 3 grams, which are triples, and 4 grams, which are quadruples. Obviously, there are no B grams and 3 grams and 4 grams overlap between the candidate and the reference. So B2, B3, and B4 are 0. And so the BLEU score for the candidate reference pair is 0. Now, yet another side note here is that there are slightly different definitions of the BLEU that also sometimes arise in the code generation problems, which is sometimes people feel it is kind of unfair if the model guessed, say, many 1 grams and certain amount of 2 grams and 3 grams, but then it guessed 0.4 grams. It is unfair to score the candidate with flat 0. So there are some smoothing functions. There is actually a set of them, like maybe 5 or 6, that can be used. And they smooth the BLEU score in a sense that if a smoothing function would have been applied for this case, then the BLEU score would be not 0, but something kind of small, but still not 0. So this introduces a it may introduce great misunderstanding, and it may introduce, and you may fail to get the results, to reproduce the results from some other papers. So if you try to reproduce some result from code generation paper and you fail to reproduce the BLEU scores, even though you think you trained everything just all right, consider taking some smoothing function, because unfortunately the things are rarely given, they're rarely stated clearly in the papers. Okay, so the 2 other natural language originating metrics are ROUGE-L and METEOR. So ROUGE-L is a metric from a family of metrics called ROUGE. So the ROUGE family was originally created for the text summarization, but then it was adopted in the translation domain. As such, some of the ROUGE papers describe some of the ROUGE metrics as purely recall-oriented metrics. While in practice, and in code generation in particular, the score for a ROUGE metric is a weighted average of precision and recall. So this is just a caveat that you might want to keep in mind. So the ROUGE-L metric that we've considered is based on computing the longest common subsequence between the candidate and the reference, the tokenized candidate and the tokenized reference. And the precision and recall are then computed as follows. This is the precision, the length of the longest common sequence divided by the length of the candidate. And this is the recall. And the metric is then given by the weighted harmonic mean of precision and recall. And we took equal weights for precision and recall, and this is the most often approach for the code generation. The METEOR metric is more involved. It is a mixed precision recall metric for 1 grams, and recall is weighted 9 times more than the precision, and it has a penalty based on the number of chunks. The chunk is defined as a set of unigrams that are adjacent in the hypothesis and in the reference. So the longer the adjacent mappings between the candidate and the reference, the fewer chunks there are. And the translation that is identical to the reference will give just 1 chunk. So if your generated code is similar to the reference, you'll get a single chunk. Unfortunately, the proper explanation on how to do the computation is outside the scope of the presentation, and I refer to the original paper. But there is one significant feature that you should keep in mind if you want to use METEOR, that the perfect meteor score for a given reference, that is meteor of R, R, can be less than 1. In fact, for a single token reference, the maximum meteor value is 0.5, but the maximum value quickly increases with the reference length. So already for like 4 token or 5 token references, the meteor score is 0.98 or so. Okay. So as I said, BLEU is the most common metric currently used for ML code generation models. It is simple to understand. It is very cheap to compute. So why not BLEU? And the reasons why BLEU may be bad and why also the other NMT originated metrics may be bad are as follows. So first reason is technical. To use BLEU for code generation task, one has to tokenize the code. Tokenization is quite straightforward in the natural language tasks, at least for the languages that I'm familiar with, while for the code, the conventions may differ. For example, let us consider sort with a pair of parentheses. This can be considered to be a single token. The whole stuff is a single token, a pair of tokens, sort and a pair of parentheses, for example, or a triple of tokens, sort, opening parentheses, and closing parentheses. Somewhat surprisingly, this is not an issue, since there is an almost universal convention how to tokenize, and it is to consider almost each special symbol with the underscores and digits being exceptions to be an independent token, to split camel case into tokens, and to take every word to be a token. So the tokenization is surprisingly not an issue. Second issue is with the exact definition of BLEU. As I've said, there can be variation with the smoothing in the smoothing function. There can be variation with the weights. So we may want to take this B1, B2, B3, and B4 in different powers. There also may be different cutoff for the number of n-grams that we consider. So for example, we can only consider only 1 and 2 grams. And all this stuff makes it really hard to compare the various models with the BLEU scores, because the choice of smoothing function, the choice of how many n-grams do you figure in, and so on and so forth, may really affect the reported BLEU score. But these are technical problems, and even if we resolve them, there are still conceptual problems that are quite significant. First of all, there is this point that the code is different from the natural languages. The code uses a small number of keywords together with the identifiers names and the special symbols with particular functions. So like we have in Kotlin, we have figure parenthesis for the code block inside if or for or something like that. And in Python, we have a hashtag for commenting out the line and so on and so forth. And it is, on the other hand, the natural language have a very large vocabulary, and with exception for these short technical words like articles and maybe some words like maybe some other simple words, maybe like exclamations like ouch. Yeah.
I'm sorry, but saying that programming vocabulary is limited is kind of misleading, I would say, because according to the latest papers, well, the vocabulary in programming is, well, in code is even larger than in natural language.
Mm-hmm.
And even if you split the tokens by like camel case and snake case, it is it still holds for some reasons, like adding new terms and mixing stuff from different natural languages.
Okay.
And so mostly it is applicable to like keywords which are super frequent, and also tokens which are not words at all,
Mm-hmm.
which are also very common, like I don't know, dots, brackets, and stuff like that. But if you're looking only at the subtokens and taking like a large enough data set of code, then most likely you will get way more than unique keywords, or not keywords, but like tokens, than in natural language.
Okay, thank you for the comment. So, all right. Okay, this point is kind of lifted from the paper on CodeBLEU, and the argument, and I do agree with your assessment, Igor. And I guess the proper way to reframe is, I mean, the point, is probably to define the vocabulary better. So, I mean, there is one definition of vocabulary, which is like if a token or word appears at least one time across the whole dataset, we include it into the vocabulary. And same for the natural language text, which is reasonable and distinct with the word vocabulary. But if I'm double guessing what the authors were trying to say, and also trying to refine this point from my own perspective, I would say that the distribution of the occurrence of tokens in programming and in natural language is different. As in, I believe that if we impose a sharp cutoff for, say, 100 most popular words in natural language versus 100 popular words in programming, then we can figure out that like all but 100 most popular tokens in programming appear way less often than all by like their share in the programming code is maybe like guess from the value like 2%, I don't know, 3%. While for the text, the tokens like all but 100 most popular words probably occupy something like 10 or 15%. So like the zip flow curves look kind of different for the programming language and for the natural language. But yeah, I do take your point. The statement is vague at best and misleading at worst. Okay, so and the related thing that Igor also mentioned is that we may argue that the keywords are different from the usual tokens. And the keywords appear more often in programming than the identifier names and so on. And the keywords may be argued to be more important or less important than the natural language, some of the natural language words. But the problem is that the natural language does not allow for, the metrics that we have considered, they don't really allow for considering different words with different significance, to giving some tokens bigger weights than the others. So this is the motivation to do some kind of, at least consider some kind of modifications that would weigh different tokens differently. Okay, so this is for the vocabulary. The second issue is that the natural languages are considered to be sequential, like humans speak and write in sequences. I'm pronouncing the sentence word by word. And many mainstream NLP models, they treat text as a sequence. In contrast, the code has natural tree structure, and the code generation models that make use of the abstract syntax tree concept are superior to the earlier models that treat code as a sequence. So the models that use AST, they at least have a great properties that they will produce at least syntactically correct code. Okay. Furthermore, the programming languages, they have very strict syntactic structure, while the syntactic structure for the natural languages is sometimes more relaxed. For example, swapping two groups of tokens in natural language sentence may not affect the meaning too much. It is especially true for some of the languages like Russian, less true for the languages like Latin, or less true for English and maybe some other languages, and less common for some, but is still okay for languages like Latin. But for the code, it is often impossible. A swap inside a code snippet will often make program invalid or incorrect. And finally, unlike a text in natural language, the code has unique semantics. So unless we have a really good model that really understands the text meaning, and it is very hard to build such a model for NLP, for natural language processing tasks, since a text meaning can be ambiguous even for a human. And an NMT metric should probably focus on the lexical precision, like the BLEU and the METEOR metric do. Whilst for the code, we have the unique semantics, and we may try to evaluate the code semantics, not as in understand the code, but as in, okay, we can build an IST and maybe we should compare the ISTs between reference and the snippet and so on. So all these ideas have motivated various researchers to create new metrics for the code generation and other code-related tasks that will take the code properties and structure into account. So let us now move on to the code-related metrics. I shall start with the CodeBLEU, which was developed by the group from Microsoft Research. It was developed to evaluate various code synthesis models. So the CodeBLEU metric is composed of 4 submetrics, and the final CodeBLEU score is a weighted average of these submetrics. So P1 is the usual BLEU4 to be more precise. P2 is the weighted BLEU1. It is a version of BLEU that only tracks unigrams and considers the keywords, which are the protected words for the as suggested the N-gran. The keywords are considered to be 5 times more important than the other tokens. P3 is a metric that measures syntactic IST match. So to compute P3, one has to compute the number of common AST subtrees between reference and the candidate, and normalize by the number of AST subtrees in the reference. And P4 is a metric that measures the similarity in the semantic data flow match. And it is given by the number of common data flows between reference and the candidate, divided by the number of reference data flow graphs. So one can immediately notice that this definition of CodeBLEU is somewhat lax, and we can vary values of hyperparameters W1 to W4 to affect the metric score. So the hyperparameter space, it was somewhat studied by the authors of the original paper, and they claim that the best performance of the metric for all of the tasks they considered, like code translation, code refinement, and code generation. So the best set of hyperparameters is W1 is equal to W2 is equal to 0.1, and W3 is equal to W4 is equal to 0.4.
Что такое number of common data flows? То есть они построили граф потока данных, и что ли, или что они дальше с ними сделали?
Yeah, so they built на английском нормально же? Или лучше на русском?
Ну, смотри, я лучше на русском, а ты можешь на английском.
Okay. Yeah, so they built the data flow graph, and they basically matched. They basically studied how they basically compared the graph. So I think they compared the edges. The edges in the data. Yeah, they compared the edges in the data flow graphs. So if the edges match, then to the hit, and they considered the edges which are common for both graphs and divided by the total number of the edges in the data flow graph.
Чтобы понять, что ребро одинаковое, надо сматчить концы в двух графах. Они как-то матчили вершины двух графов между собой?
Yeah, they did. So there, I mean, what they did is that they took the leaves to identify the variable sequence. Then they anonymized the variables. I don't know what's the proper word. Basically, they called every variable like var_i according to the order of its appearance in the data flow item. Yeah, and then they basically matched what's going on with the variable. Like variable was taken at point 1, then it was altered at the point 2, then it was used at the point 3 to modify the other variable, and so on and so forth. So yes, that was okay. So, all right. The other metric that we've considered is Ruby. So Ruby was developed by Tran et al. For the code translation, also known as code migration task. It is composed of 3 metrics. So unlike CodeBLEU, Ruby works in the fallback fashion. So the metrics are applied one by one from the more advanced to a more simple. If the more advanced metric cannot be computed, then we use a more simple metric. So the most involved metric is GRS, which is comparing, which is basically measuring the similarity between the program dependency graphs of the reference and the candidate, using the approximately computed edit distance between the 2 graphs. If the program dependency graph cannot be built, however, if the program dependency graph cannot be built, then we employ the TRS submetric, which calculates the similarity between the AST of the candidate and the AST of the reference, using the edit distance between the 2 trees. I should notice that for the datasets and models we've considered, we never had the case when we can not compute the GRS, but we can compute the TRS. Finally, if we also cannot build an AST, then the metric score is given by the STS, which is a string edit distance between the tokenized reference sequence and the tokenized candidate. And as such, it can be always computed. And a particular feature of Ruby that you should keep in mind if you want to use it is that GRS and TRS may take some time to compute, at least in my experience. So when you're evaluating the dataset, you may want to balance between the long time of execution, which was circa 30 minutes on CoNaLa to get graphs compared for every snippet where graphs can be built, and you should balance between the time of execution and the necessity to fall back on the STS metric sometimes if you want to make the evaluation faster. Okay, so as you can see from the Ruby definition metric definition, that for the short snippets, this comparing ASTs and program dependency graphs is tricky because ASTs and PDGs, they're relatively small, and a small change in the candidate can heavily affect an AST and a PDG, and so it can heavily impact the score. And another possible issue with with Ruby is that the string edit distance metric seems to be kind of simplistic. It doesn't account for the adjacency factor, so we don't really care about the bgrams and so on. And this was really important for the designers of the NMT metrics, and they underline that this is really, you really need to consider that you really need to take care of the fact that the adjacent unigrams in the reference should also be adjacent in the candidate. So this stuff motivated us to create a metric that would be a mixture of Ruby and BLEU. So better names are welcome. And Ruby BLEU is actually a pair of metrics. It is a weighted combination of one of the Ruby metrics and BLEU. So the weighting is done in the following fashion. So we have an exponential weight here for the Ruby part of the score, and basically the longer is the snippet, the higher is the weight with which we consider the GRS score or TRS score, whatever we consider in our, whether we want to consider GRS or TRS depends basically on our choice. And the weight, we have studied empirically what kind of weight should we put, and the best results were achieved for the weight being 800. And S here is the sum of total sizes of the reference and the candidate program dependency graphs or ASTs. And here B is the BLEU score. And in the case when the GRS or TRS cannot be computed, we simply fall back to the BLEU score. Okay, so Ruby and CodeBLEU, they seem to be quite nice. I mean, they were created with code in mind. They are claimed to be good for the code-related tasks, and CodeBLEU is claimed to be good for the code generation tasks in particular. So why don't we use them by themselves as they are? Why do we need to study them? So the problem is that they hardly have been studied. And there is, for the CodeBLEU, the dataset is really strange. So the inputs are the natural language documentation, and the class environment the code resides in. And the environment is made of two lists of entities: class member variable names with their data types, and member function names together with their return types. And the output is a piece of code of the desired class member function. So basically, we are given like a good amount of details about the function, all the variables and the data types, and natural language documentation. And outside we get a function, which is kind of not exactly the setting in which the other code generation models are compared. The typical code generation dataset is a natural language intent, like just a natural language sentence or maybe several sentences, and a programming code output with no data on desired, like on the return types and function names and so on. And the problem with this dataset is that the models that have been studied on it are significantly different in quality. So as I said earlier, I mean, if we have really different qualities, then almost any metric can be good. And this indeed was the case for the CodeBLEU paper. As for that paper, both BLEU and CodeBLEU metric were good enough to distinguish between every pair of models. So it's like, it's not the added value of having CodeBLEU is unclear, because BLEU seems to be working well enough. And I mean, CodeBLEU is just more costly to compute. They claimed high human metric correlation coefficient for the CodeBLEU, but the human metric correlation coefficient in the CodeBLEU paper is too high. First of all, they used Pearson correlation coefficient, which is kind of a strange choice, but okay, whatever. But second, the correlation coefficient is greater than 0.9. And this is not in line with the correlation coefficients that one could typically expect in some other kind of studies. And it's not the size of correlation coefficients that we saw in our studies. So this seems to be dubious. I'm not saying that there was something fishy in what they did, just maybe that the data set is very peculiar. And for the Ruby, there isn't even a proper study for the code generation. There's only one paper on Ruby with one data set on code translation, only 9 projects in the data set, and the project and the models that are compared are also quite significantly different in the quality. And also for every data set by one, for every model by one, Ruby BLEU is able to distinguish between the models in the same way as Ruby does. There is one artificial data set on which Ruby works better than BLEU, but it is very strange. They basically took a real data set and then they kind of reverse engineered the outputs in such a way that the BLEU will fail. And I'm not sure how real, whether one can really see the outputs like in this artificial data set in the wild. Okay, so let us move on to our datasets and models that we studied. So one big problem with studying code generation is that there are not enough publicly available models. And we had studied 3 different datasets: CoNaLa, Django, and Hearthstone. And for each of them, we had 2 to 4 models available. And basically, that is not enough, because there are many more models which with some claimed results being published in the papers, but no realizations of these models are available. And it's not even fully clear how to get these models similar to what did the authors do. So this is a big problem. This was a significant problem in our research. So let us start with the CoNaLa dataset. The CoNaLa dataset consists of 2,879 examples, which are split into 2,379 training examples, 0 in validation, and 500 in test. It has been crawled from Stack Overflow and then manually curated by the human annotators. So it's for the CoNaLa dataset, the intents are really quite well written, and the reference snippets are always quite to the point because they've first been voted as the best answers, like maybe second best answer by the Stack Overflow users. And then they have been also manually curated by the annotators. There is also an additional automatically mined dataset with like 100,000 examples from Stack Overflow. And some of the models that we considered, they use this automatic dataset for training, but it's not used for the test. And from our research point of view, it has several features. So first of all, it has a sound variety of intents that cover many different methods used in Python. And this is kind of nice. And the intents in CoNaLa are detailed and written in natural language. And I mean, which distinguishes it from some other datasets. For example, in docstrings, the intents are very short. And in many cases, even a human programmer will have problems with writing code that would be similar to the reference, given the intent from the docstrings. There are 4 models available, which is nice. So as we can do more pair comparisons. And the current state of the art models evaluated on the CoNaLa have BLEU score circa 22. And so, this means that some of the test snippets generated have very high quality and many others have very low quality, and human graders can distinguish them. This is good because if the snippets, every snippet would be very good, or every snippet would be very bad, it would be hard for human graders to distinguish to say that, okay, the snippet is very bad and the snippet is not that very bad, because human graders can't really grade on a 0 to 100 scale. The CoNaLa snippets are very short, and the absolute majority of them is 1 line of code. And so this limits the possible usability of the metrics that use the code structure, the CodeBLEU, the Ruby, and the Ruby BLEU. And the 4 models we evaluated on the CoNaLa, one of them is sec-to-sec baseline model, which is significantly worse than the other. And 3 other models are transformer-based models, which are quite close to each other, both in the results and in the design. And so we had a hope that as the results of these models are close, we may see that some of the metrics fail to distinguish between the outputs of the models. Okay, second dataset is Django, which is a corpus that contains 18,805 pairs of English pseudocode intents and corresponding Python snippets. So every Python statement is usually a single line of Python code, and it's split into train, validation, and test as follows. And the intents are written in the pseudocode that can often be translated into Python code with hardly any changes. So there are even cases like the intent is if, and the code is, well, if. And this simplifies the code generation task. So the evaluated models get higher BLEU scores. The average BLEU score is circa 75. But this reduces the generality of the conclusions that we can draw from these results. And the pseudocode was generated from the snippets of code written for Django, which is a web application framework. So we can't really draw very general conclusions. And it is very hard to perform a human evaluation of the generated snippets, because snippets are pieces of the large framework, as they're not self-contained. Sometimes they are literally one line from a big method. So we opted not to do a human evaluation for the Django dataset. And the generated snippets are a single line of code with simple structure, and not always it is possible to build an IST because they're, well, not self-contained. So the CodeBLEU and Ruby usability is probably limited. Okay. The third dataset we considered is called card-to-code or Hearthstone. Well, okay, it's called third dataset is Hearthstone. It is from the pair of datasets that are based on the collectible trading card games, Magic the Gathering and Hearthstone. And the Hearthstone dataset is more popular in the community, so we've focused on it. So the dataset contains 665 pairs of Hearthstone card descriptions and the corresponding Python snippets. And the Python snippets are the classes that can be used in the Hearthstone simulator game Heartbreaker. And the dataset is split as follows. So the dataset has the following features. So as intense as the descriptions of the Hearthstone cards that should adhere to the Heartbreaker notation, the generated code has a relatively rigid structure. So basically, a well-trained model probably guesses 60 to 70% of the code to be written immediately, because it is the same for every intent. The code generation problem is very peculiar. So once again, the conclusions we can draw are very limited. The generated code is relatively long and complex, so it is plausible to expect that the CodeBLEU and Ruby metric performance may be different from the statistical machine translation, and then that they may be performing better. So for the Hearthstone, we had two models. One is one uses LSTM and AST, and one is based on the convolutional neural network and also make uses of the grammar. And for the Django, we had three models. Two of them are transformer, which are closely related to each other. And one of them is also LSTM plus AST. Okay. So the research question we posed there as follows. How suitable are the metrics we considered for the code generation models assessment? So as we discussed, this question is hard to answer in general. So we expected to get some insight from our results, like to see where metrics fail, how they fail, why they fail, and try to formulate maybe some ideas on why they fail. It's not probably stuff to be written in the paper, but it may give us ideas on how to create a better metric. Second question is, how significant are the metric scores, and how large should be the difference between metric scores to claim that one model is better than the other? So here everything is quite simple, as in we want to compare models also in the terms of statistical significance, and not only in terms of raw scores. And we need to do a small study in statistics. And the third question is, what is the degree of correlation between the human assessment and the scores of the models? So there is a typo here. It's not blue, it's just any metric scores of the models. Once again, we want our metric to be to emulate human judgment as close as possible. So naturally, we want to study that. Okay. So the research methods they were as follows. First, we trained the models, we collected their outputs and evaluated them with the metrics. Then we carried out a Wilcoxon signed rank test for the metric's statistical significance. We basically wanted to check that the how significant are the difference in the scores. Afterwards, for CoNaLa and Hearthstone dataset, we carried out the human evaluation of the outputs. So this task is still in progress, so please join us. It's kind of fun, and we'll be glad to pay you some money. We'll be glad to pay you some money for helping us. Afterwards, we aggregate the human scores to obtain the ground truth, and the aggregation was carried out according to the common according to the common method of aggregating by Riker et al. And finally, we computed the correlation coefficients. We computed Spearman Rho and Kendall tau to measure correlation between the metrics and between the metrics and the human judgment. Okay, so I will not try to present the whole set of our result in the table forms, because they're just too many digits, too many numbers, and they had to be understood in a few minutes. So I will just give you the gist. So the gist is as follows. So the humans are actually quite good for distinguishing between models, and so is the METEOR metric. So humans and METEOR distinguish between every pair of models we've considered with at least 95% significance, according to the Wilcoxon test. And BLEU failed only on one pair for the Hearthstone dataset, which is still kind of okay-ish, since the Hearthstone dataset is only 65 test snippets, and well, it's only 66 test snippets, and the BLEU scores were quite close. For the two models, they were like 72 and 73.5. And for the rest of the models, BLEU, for the rest of the models and datasets, BLEU, humans, and METEOR were able to distinguish between the two, even when the BLEU scores were quite close. So for Django, there were two models with BLEU scores like 71.7 and 72.1. So the difference in BLEU scores for like 0.4 on the scale from 0 to 100. It's like 0.4%, maybe 0.5. And yet BLEU, METEOR, and human were able to distinguish. The other metrics performed not so well. Surprisingly, the worst performance was by the CodeBLEU and the Ruby metric, by the code-related metrics. And they were also not so good on the Hearthstone dataset. Both Ruby and CodeBLEU couldn't basically predict anything on what model is better and what model is worse. And the mixed Ruby BLEU metrics that we considered is okay, but it's still slightly worse than BLEU, or maybe on par with BLEU, and definitely worse than METEOR. So it's still not. So from our results, from the statistical significance, it is unclear why one should use CodeBLEU, Ruby, or Ruby BLEU. On the correlation, once again, I'm not going to report you the raw correlation figures, because they're different for different dataset, which is reasonable since the different datasets have different size of test part. But the overall trend is for any dataset, the correlation, and for any model, the correlation between two human graders who graded the whole dataset, that was me and Igor, the correlation was better than between any metric and any human. The natural language metrics, they have higher correlation with the humans than the code-related metrics. The worst overall correlated metric is CodeBLEU. The next comes Ruby, then Ruby BLEU, and then the NMT metrics. The NMT metrics are very well correlated between each other, better than the humans. And the code-related metrics have mediocre correlation between almost anything. And an important thing to notice is that the difference in correlation between NMT metrics and humans, and between two humans, is still kind of significant. So say for the CoNaLa dataset, we have that between me and Igor, the difference, the candle tau was 0.62, and the Spearman row was 0. The candle tau was 0.56, and the Spearman row was 0.62. Well, if we compare like the best performing metric in terms of correlation with human, which is BLEU, it has only 0.1 correlation, only 0.51 correlation coefficient Spearman row, and only 0.4 for candle tau. So it's like well, it's not a proper way to compare correlation coefficients, but the difference is like 20 to 40%. I mean, it's not appropriate way, but kind of we can see that the correlation between any metric and a human is not as good as between two humans. Now, these things may change because we still have to collect some data, because basically we had two graders who graded the whole data set, me and Igor, and a few graders who graded some small pieces of data sets, like 1/10 or maybe 1/5. So in total, we have like in average, 3 grades per snippet, which is not so much. And we also may have a significant bias coming from either me or Igor. So maybe this result will change. Okay, and the last outcome, which is interesting, is that the slight variation in the dataset corpus strongly affects the outcome. So there are 2 points that I want to mention. First, in the CoNaLa, there was a slight, for some tasks, there were more than one reference available. And we have considered changing references, like to check what is a possible way to, how shall change the p-value of the statistical significance of difference in scores between two metrics. And it turned out that, I mean, if you have two references, and both of them are perfectly fine and perfectly valid, and you consider only one of the two for one case and only the other one for the other case, then statistical significance can change a lot, from like 0.005 to something like 0.02. This we saw for the BLEU scores in one of the cases. One can still argue that in both cases it's still less than 0.05, but well, I mean, if this would happen if this would bump results from 0.03 to 0.06, then it would be problematic from the common way of statistical understanding in some way. And another point is that you can do some kind of adversarial selection of the corpus. So you can take a whole test dataset for CoNaLa, which is like 472 snippets when you account for the duplicates. And then you consider how many snippets you can leave, so that for some pair of models, the BLEU scores will revert, and you will have, so on the full dataset, model A beats model B with at least 95% significance, but then you leave some part of the dataset, you do like an adversarial search, and then on this adversarially selected piece of dataset, model B beats model A instead with a 95% significance. And it turned out actually that that for some models you can like leave 90% of dataset intact, so like throw out only 10% of the snippets, and the performance is reverted. So I'm not sure what does this mean in the larger picture. I guess it signifies that we should carefully create the data sets for the code generation, but it also may mean that some of the way of the current way of comparing the models may be somewhat wrong, as in we don't really maybe some of the models which are worse according to CoNaLa than the others, they're in fact better than the others. Okay. So future work. What is still left to do? We still have to get more data from the human assessors and incorporate it to get better data on statistics, on the correlation. We want to do more statistical tests for the metrics. So we want to do a better version of Wilcoxon that will. So the common version of Wilcoxon test that is used, it believes that every single point is independent. Well, this is not exactly true for the comparing of for the model comparison. I mean, every snippet was treated by several models, so the score of different models on the same snippet are correlated. If the snippet is very hard, probably all the models will fail. If the snippet is easy, probably the models will perform better. So if we want to so this issue came to our attention very recently, so we still didn't do that. But the expectation is it won't really change anything. And we also want to do the t-test. because in some papers it is claimed that the t-test is more statistically robust than the Wilcoxon. We also want to study why exactly CodeBLEU and Ruby fail. So far we have some anecdotal experience on when Ruby fails and when CodeBLEU fails, but we still want to understand it better, and we want to make some prescription for like how to make which pair of reference and snippet make CodeBLEU fail. And then we want to use this idea to create a new metric. Now it's really hard to create a new metric. I don't really have any good ideas by now. I had a shot of that maybe mixing Ruby and Blue will be good, but it turned out that it's not so good. So I guess unless we really come up with bright ideas, we won't really try to create a new metric. Turns out that it seems that it's really hard to create a new metric. And finally, if you wanna, if I wanted to summarize the talk, I would say that the code generation models are still in the very early baby steps. That the metrics for the code generation are not so good. That if you want to measure the quality of your code generation model and report it in the paper, you should probably use BLEU because everybody uses BLEU. If you want to have some metric to improve your code generation model during the training, you should probably use METEOR because it seems to be the best performing metric. And there are many pitfalls in creating a metric and understanding whether the metric is good or not good. So I hope that I elucidated at least some of them for you, and I thank you for you coming to this seminar. I will be glad to take any questions.